Welcome back. We're going to dive straight into finding out more about electromagnetic induction. But just to make sure that we've tied all the loose ends together, let's just revise a very important term from electromagnetism. And that term is magnetic flux. It is a kind of a difficult word to describe or term to describe, but it is very important. So it helps us link the idea together of what's happening in terms of the magnetic field. So remember, we've got a magnetic field which we can represent as B. This is the magnetic field strength. And so when we look at this, the way we represent B is by field lines. So around a bar magnet, for example, you would recognize you have a north end and a south end, and you've got these field lines that are going to run out of the north and in at the south, and they're going to form this butterfly pattern that we like to refer to. And we've even got some field lines that run out at that side, and they're going to run in at this side, and we've got this big loop of field lines. Now, those field lines are related to the magnetic field strength. We recognize where the field lines are close together. So in this area here, we've got the field lines nice and close together, and we'd say that's where the field lines are strong. Over here, there's just one field line, it's weak. Bear in mind now that magnetic flux is not just the field, but magnetic flux is defined as B times the area that is at 90 degrees to the field lines. So it's the area that the field lines cut through. So at that point, the field lines are all passing through this area. And we'd have to look at how closely those lines are packed together to get an idea of magnetic flux. If that field line is not at 90 degrees, then we introduce a mathematical term which we say is cos theta, which will help us work out what is the component of the area as if it was at 90 degrees. And so when we're working out magnetic flux, remember the symbol for magnetic flux is phi, and we're going to say phi is equal to B times A times cos theta. And in this case, in our case that we're going to look at today, we're going to be looking at the area that's at 90 degrees to the field lines. And you'll see that that's not particularly difficult to imagine and to see, and we're going to be applying that knowledge to a particular situation. So we've covered magnetic flux, and we've got a good idea now. Just to remind us in terms of how we get magnetic flux. And we've used the example of a magnet, a bar magnet, but it doesn't have to be a bar magnet. It could be a conductor that has got charges that are moving in it. In other words, a conductor that has a potential difference across the ends, and there are free moving charges or a current that is passing through that conductor. And we've shown in previous lessons that moving charge or a current is going to be able to produce magnetic flux in an area around the conductor. Now, that conductor could be a straight conductor, or it could be a coil, but around it, there is this area that the field lines pass through it. And we've used the crosses and dots to represent that magnetic flux, or those magnetic field lines, and we've been able to say where they're close together, high magnetic flux, where they're further apart, low magnetic flux. I hope you remember that. Now, this was the state of affairs in the middle of the sort of 1800s. The kind of people had been playing, Ørsted has been playing with working out magnetic fields around a conductor. And this physicist from one of the Scandinavian countries, it was a breakthrough to be able to see that there was a relationship between electricity and magnetism. But the key idea was, is there a way to use magnets to create electricity? Because again, at this stage, they only had very primitive cells, batteries, electrochemical cells. And they weren't very reliable. So people wanted to have electricity. And the idea was, let's use magnets to make electricity. And the man that came to the rescue was a really important physicist. He came from a very poor background. His name is Michael Faraday. He wasn't even supposed to be a scientist. But he worked out that if we take magnets and we allow the magnetic flux to change, and we allow the magnetic flux by either changing the position of a coil, so you can move a coil, or you can move a magnet. If you move either of these, then guess what happens? You induce an EMF. If the coil is just a coil that isn't connected in a closed circuit, it will produce an EMF across the ends. But if we connect it into a loop, into a closed circuit, then we will get a current induced as well. And we would say, if there's a current induced, then we've got moving charge. So this is converse thinking. Initially, we said moving charges produces magnetic field. Now we're saying, let's change the magnetic flux, move the magnets or move the coil in the magnetic field, around the magnetic field. And what do we get? We get an induced EMF, a moving charge, if it's a closed circuit. And that's really important for us. So let's just go and explore this. Now, we can't do it in detail, but we have a simulation. So let's go and have a look at the simulation. Here's my magnet. And what I want you to see, I've made it really simple. I've connected this coil to a light bulb, and I'm simply going to move the magnet in and out of the coil. And what do you notice is as I do that, the light bulb goes on and off. Now, if I turn the magnet around, it doesn't make any difference. It still goes in and out and making the light bulb shine. Now, you might say to me, what happens if I do it above and I don't do it in the coil? Well, the light bulb still goes on and off, but not to the same degree, because it is better if it goes through the middle of the coil. Okay, so that's quite interesting. We can also just do a little experiment here, is if I put it through a smaller coil and try and move it more or less at the same speed, you'll see the light bulb's going on and off. But through the bigger coil, it looks to me like the light bulb is burning brighter, or is indicated to be burning brighter. So as we do this sort of experiment, there's lots of observations and things that we can start to look at. The ways of trying to explain what's actually happening. So let's go to summarize some of what we've seen. And the first thing that I wanted us to look at is to say, well, what are the factors that affect the induced EMF in a coil? Now, at this stage, I'm just using the light bulb, the shining light bulb, as an indication of how strong the EMF is. If the EMF is very big, then the light bulb will shine brightly. We know that's the case. If you have a 9-volt battery and you have a 1.5-volt battery, the 9-volt battery is going to give you a much brighter light bulb. And so we're not making things up here. We recognize that the induced EMF is going to be bigger if you've got a bigger number of turns in the coil. You've just seen that. But are there any other factors that we might consider? Now, this next one, we're going to need to go and have another look at the simulation, and we're going to have to look at how the magnetic flux changes in the coil. So the change of magnetic flux in the coil. And this is something that Michael Faraday took a long time to come to explain and realize, and it's part of the statement of what we now know as Faraday's law. So let's go and have a look at this and adapt our simulation a little bit. I'm going to put in some field lines, and I'm also going to put in a voltmeter. So I'm going to revert to just one coil, and at the moment I'm going to change it around as well, just to have the North Pole over here. So as you can see, the field lines close to the North Pole, there are lots of them, they're close together. So what do we know? That's lots of magnetic flux. Now, if you compare the amount of flux that is going through the coil in that position, what would you say about the amount of magnetic flux? Well, I think you can see it's hardly anything. But if we bring the magnet closer to the coil, push the magnet into the coil, then the amount of field lines cutting through that area in the coil, that magnetic flux, is going to increase. And even the ones that are cutting past the wires of the coil, they will increase here. So these curved ones cutting through the wires, they're increasing. So if I move this, you recognize this is a low position of flux. And if I move it to that position, you'll see that there is more flux through the coil at that point. But what do you notice at the moment? As I've changed those positions, the reading on the voltmeter and the light bulb aren't glowing. It doesn't look like there's much happening here. So yes, the flux has changed, but there doesn't seem an impact. That's because of the next idea, and that is that it's all dependent on the change in magnetic flux. Because at the moment, is that magnetic flux changing? No, it's the same as it was a second before. It's not changed. But watch here. From that position, low magnetic flux, watch what happens to the needle as I do this. High magnetic flux. Now I've stopped. But in that point between low and high, there was a change in magnetic flux. You know, if your marks start off at the beginning of the year and they're particularly low, and they, over the progression of time, they increase, that's a big change in your marks. And that's exactly what's happening here. There's a change with respect to the magnetic flux, but also with respect to time. But now it's staying stationary because there's no change. So only when there's a change in magnetic flux, and that's the important thing. Either the coil has to be moving or the magnet has to be moving for us to appreciate a change. And I hope you've got that idea. So if you take a careful look, and you look carefully here, if I do this, you'll see I'm changing it continually. And the light bulb is flickering on and off. So as long as there's a change in magnetic flux, there's going to be an induced EMF. Now, the last thing that I want to just say very carefully here is it's not just about the change in magnetic flux. It's also about the rate of change. And when we talk about the rate of change, we're talking about a measure of time. It's about how quickly or slowly the change takes place. So have a look here. I'm going to deliberately move this magnet into the field very slowly and out very slowly and back again very slowly. And you'll see there was hardly any movement of that needle. Now what I'm going to do is I'm going to move it quickly as I can. And you can see that it's jumping backwards and forwards in a much bigger way if I move it just backwards and forwards over here. Because there's a bigger change, or the rate of change of magnetic flux is bigger. And so that helps us to understand the factors that affect our induced EMF. And so we've looked at the change. Remember, there has to be a change in the speed of the motion gives us the idea of the rate of change. And so here, let's put it all together. Faraday's law says the EMF induced in a coil is directly proportional to the rate of change of magnetic flux. And we use this equation. E is equal to the number of turns. There's a negative sign outside. The change in magnetic flux divided by the change in time. And we've said the flux is the field strength times area times cos theta. Don't go away. We'll be right back. Take a short break, and we'll see you soon.